The problem statement that I have picked in the company is real-time card payment fraud detection within Chase. So this is an extremely high volume card and digital payments. In recent years, fraud attempts have become more sophisticated and at greater speed. Existing ruled or legacy fraud detection system often resulted in excessive false positive, causing legitimate payments to be declined or requiring step-up verification. So some of the machine learning that is attractive in this case is pattern-rich data, high business value and feasibility and proven success, where each transaction contains numerous features such as amount, merchandise, device location, where machine learning models can leverage these features to identify subtle fraud patterns, also can improve fraud detection, which leads to direct fraud losses and better customer experiences, where it has already been reported significant cost savings from utilizing AI in fraud and risk management. For the systems that are already in use at Chase within CCP demonstrating that it is practical and high impact use case. Some of the crisp DM business understanding, defining the problem, business problem. The core question is how can Chase more accurately and quickly distinguish fraudulent from legitimate card payments in real time to reduce fraud losses and customer disruptions. Determining problem, the objective is to develop a model that assigns a fraud risk score to each payment transaction with historical label data. The score will support smarter real-time decisions, approving or declining or requiring step-up verifications. So defining the success, business outcome metrics, reduction in net fraud loss dollars and fraud rate per thousand transactions, lower false positive declines and fewer customer complaints, also reduce manual review. Some of the model performance metrics, precision and recall for fraud at the operating threshold, where we can lift compared to the business rules. Some of the identifying relevant features include transaction level features, where we can focus on amount, currency, merchandise, merchant ID, device type, IP address, geolocation, for example, and also have this customer behavior features like historical spends, average ticket size, typical merchandise, or recent travel flags, prior fraud histories, tenures, credit limit, and utilization. Some of the contextual features include velocity metrics such as the number and value of the transactions in recent windows. So the solution validation plan concept. The proposed solution that I picked is a deploying a supervised machine learning model such as gradient boosting or deep learning trained on historical label transaction. The model will generate a fraud risk score in real time where we can trigger declines or step up checks, while low risk will enable automatic approval, potentially overriding. The iterative validation experiment requires offline backtesting, shadow deployment, controlled A/B testing, qualitative validation. All of this performance can against the existing rule engine with the historical data. Some of the score live transactions are in parallel with concurrent system. And also route a small percentage of payment traffic to the ML plus rule strategy, where versus rules only over several weeks. And the qualitative validation, where we collaborate with fraud analysts and operation teams to review model explanation in edge cases and ensuring the system is both usable and trustworthy. Some of the machine learning system design, cloud versus edge deployment. The solution will utilize cloud or data center deployment instead of true edge deployment. This approach is necessary because fraud scoring must be fully integrated within the bank's central payment processing and also comply with high availability and governance required. Offline versus online. Offline learning with regular learning such as weekly or monthly will be used since fraud labels are delayed due to chargebacks and investigations. This method not only allows for the rigorous evaluation before updating the model, but also online may be considered in the future for fine-tuning. One other thing we have is batch versus online production, where we can inference with employed for each transaction, because card payments require approval or decline decisions with milliseconds. The latency, SLAs, and high throughputs need the systems to perform in the architecture with low latency model serving and feature computation. Potential risk in the production: data drift and concept drift. Fraud patterns, merchant behaviors, and customer channels continuously evolve. So we could altering input distributions and the relationship between the features and the fraud. Training serving skew. Inconsistencies between how features are computed offline in real time, such as changes in aggregation windows or missing data handling, can result in inconsistent score. Coming with latency and availability, the model must deliver responses within strict time constraint and maintain high availability. Outages or slower responses could block payments or necessitate a fallback to less effective rules. Label noises and delay. Fraud labels often arrive late and can be disrupted, introducing noise and slowing the learning of the new fraud tactics. Robust labeling processes windows are essential. Fairness and customer impacts. There is a risk of disproportionate false positive affecting certain geographies or customer segments. Governance and fair assessments are necessary to prevent unintended bias while still ensuring the security of both bank and its customers. So this is a problem statement I have picked, and this is how we can use ML with different variations in ScriptDM across the channels. Thank you.